Welcome to Natural Habitat Adventures Daily Dose of Nature. Today's topic, Nature's Decoders, Illuminating Ice, presented by NatHab Expedition Leader Nikki Sentinella. I'm your host, Rob Mess. Thank you so much for being here with us today. Over to you, Nikki.
Thank you, Rob, and hello, everyone. G'day, as we say over here. I am Nikki. I have done a few of these Nature Decoders series, and the Nature Decoders series, we've been sort of looking at general aspects of the world that we can see regardless of where we are, either living or traveling to, and getting us on the same page with some of that contextual information and getting into the nitty gritty a little bit. So today we're going to talk about all things ice. We're going to talk really focusing obviously on our glacial ice and our sea ice, which are our most abundant forms of ice, as we'll see. And I'm presenting today from a Wawaka land in Australia, the land of so much ice that we have one range of mountains called the Snowy Mountains. So rest assured, I have been up in Canada for a while. I am also an expedition leader with Natural Habitat Adventures, as well as a biologist in my non-guiding time. And so I have had some experience with the ice as well. But it's a really interesting global topic, as we'll learn, and it's part of a really big cycle that affects all of us and the whole planet. Us being the blue planet, ice is really, really important as part of that process. So we're going to dive in, and these are just some of the topics we're going to have a look at very briefly. We'll see some really beautiful scapes in the background as well, and they're from the recent Greenland trip. And these are by our other EL, Anthony Amsel. So a lot of those beautiful photos are from him. Thank you. Today we're going to ask what is ice, which seems like a really silly question. We all know what ice is, but we're going to break it down, have a look at it at a bit of a molecular level, and talk about how that forms. And then we're going to look at a little bit of detail of the water cycle, because the water cycle is really important when we're talking about ice and global weather patterns. And then we're going to dive in and look at some of the more specific intricacies of types of ice. We're going to look at glaciers and we're going to look at sea ice. What are the differences? What defines icebergs? And then we're going to have a little bit of a look at what ice is doing today, some of the trends that we've seen over the past decades and centuries, and a little bit of a northern ice condition report, very simply, just to see what it has looked like. It is August now, and we often see our last ice in July or August, and we saw it in July this year. So we'll have a look at that up in the northern hemisphere. And then, as Rob mentioned, there is the opportunity to ask questions, and I really encourage you guys to submit any of your questions that pop up in your mind throughout the webinar so that we can have a look at them at the end, and I'll do my best to answer them. All right, so what is ice? Seems like a silly question, as I said. Ice is solid water, so we are looking at water. It's one of the four if you count plasma, states of matter that we can see even in like a picture. If you have a glass of ice water anywhere, there's always going to be the three forms of water because we're going to have our solid water as our ice cube, we're going to have our liquid water, and then undoubtedly there's often some water vapor around us at some point. We feel that in humidity. And so there will also be this gas form of water as well. And we can see that as we get condensation on the side of our glass, because that glass is getting so cold, we're actually picking up that water vapor and it's turning into liquid water as it changes state. So water's all around us and it's really important. Water is H2O, and it is one oxygen molecule, and then it has two hydrogen molecules around, represented by that big red circle in the bottom left, and then the two hydrogen molecules on the side. And they do form this angle of pretty much exactly 106 degrees, 106.6 degrees. which I love that we know. And it's not something that I have figured out in my physics and chemistry times. But what we can see from that is the way that water arranges itself as a molecule, and that manifests in a way that we see these hexagonal patterns. And so if you think of any ice crystal or snowflake even, we often see this hexagonal pattern, and that's because of that angle and the structure in which the ice grows. So this ice is a crystal structure. It's a lattice of all of these water molecules stacked together in quite a neat way. And you can see this sort of 3D representation in the center here. And so when we get this loose crystal structure, it actually has a fair degree of air within it. And so this is why our ice cubes float, this is why our icebergs float, and this is why our sea ice floats, which is really important, as we'll get to later. It is less dense than liquid water. So at atmospheric pressure, it's about 8.3% less dense than water. And so we do actually see a volume expansion in the space that it occupies. Because that ice is expanding, it will take up more space than the water it is in. So you may see this when you fill up your ice cube tray at home. If you put water all the way to the very top and then you freeze your ice cubes and you take those ice cubes out, and you can see they've all sort of connected and overflowed because that ice is expanding. And it's the same reason that when we put vegetables in the freezer, they come out mushy because those cells have expanded. They've actually broken the plant cell wall, and it ruins the integrity of that plant. And so with that expansion, I have been asked before, well, then if ice is taking up more room, then if it melts, then we'll have more space. So shouldn't we see sea levels drop? And the answer is yes, if all of the ice was in the ocean, but it is not. Majority, large majority of our ice is on land. And so when that ice melts and it goes into the water, you're now adding extra fluid into the mix. So we are seeing sea level rise, just as a global scale to think about. Because sometimes when we look at a really small experimental idea of like water melting or freezing in a glass, we sometimes forget about the context. So just one thing to point out. One thing that I always find nice and interesting as well between our liquid water and our ice as it starts to freeze is our water is densest at 4 degrees Celsius. So just above the freezing point of water, it's actually where the molecules of water sit closest together before you start to get any push of small ice molecules forming. And that lattice is now starting to expand, and so that water will become a little bit less dense before it actually freezes, which is just a nice little fun fact. So I took this photo from the inside of my windscreen when I was living in Canada, and I had these beautiful little ice crystals growing, and I've zoomed in this photo and just circled a couple of them. And if you look really closely, and you can see it in some of the other fractals that are forming, you can see that hexagonal pattern. And I urge you to look at your next perfect snowflake, and you'll see these beautiful six-way structures as that ice grows out. So it's just a fun thing to look at. Obviously, if that ice is then growing and forming in certain directions and it runs into another piece of ice that's starting to form, then it will start to change that direction. So often looking at those smaller ones that haven't been interrupted, we can see that six pattern really clearly. So that's our solid ice. That's our H2O molecules moving around and forming these beautiful structures. But where is this water and how is it moving around the world? And we look at this through the water cycle, sometimes called the precipitation cycle. That's how I learnt it at school, which I don't know why, because water cycle is much easier and more informative. Precipitation is just one form of movement of the water in the water cycle. So this is a really amazing diagram, and it is in the public domain, so you can put it as a poster on the back of your bathroom door if you want to study it. That's how I studied a lot of my notes as a kid. And so there's a lot of information here, and I'm not going to go into all of the detail here, but it does show you a lot of the movements of water. The main things that we're looking at, obviously, we have our huge oceans and then we have our land masses. And so we have majority of our water is in that ocean, but it does move up onto the land. And it moves up onto the land through that evaporation, turning into that water vapor, being lifted up into the air and then moving through the atmosphere, where it then falls often back into the ocean, but then also onto land. And so we're seeing this upward drag of water coming across and then being placed across the landscape. Where it falls, when it falls, and the temperature at which it falls will change the way that water is formed. So obviously when it's cold, we're going to have our snow, and we're going to see those higher areas accumulating more snow and ice compared to our lower areas where they're going to fall in the form of water. We see some cool things when we get some cold temperatures or some pressure changes where we see hail. We see that ice falling in a warmer area. That was always the closest I got to snow as a kid in Australia on the coast, to the point that when we sometimes had big hailstorms and we had like a fine size of hail, I'd collect it and keep it in the freezer. It was very exciting. So it will fall in various places and then will come down following the path of least resistance down through rivers and waterways. It'll either get trapped in the form of lakes where it will pool before making its way out, or it will continue to flow straight through. The other thing I want to point out in this diagram is the groundwater. We do have a lot of groundwater that seeps and permeates through our soils, through our rocks as well, gaps in the ground. And some of that water is renewable in that it will move within that layer, depending on what the Earth substrate is. We will see some evaporative effects from the land, but what we more see is we see transpiration from the plants. So plants are going to use that water, they're going to draw that water up through their roots, and they're going to transpire that into the atmosphere in the form of water vapor again. So that is going to draw the water out of the ground, and then when it rains, it's going to go back into the ground. So we see a little bit of a renewable water cycle within the ground. However, once we get deeper than that, once we get below that active layer of groundwater, we have reservoirs of groundwater and they're not renewable. They actually stay in the earth for a really long time, and we'll look at those retention rates on the next slide. So you can see there's a lot of movements happening. We're seeing evaporation on land and water, and we're seeing the water falling in different places. So it's really important that when we think about ice and we think about water, we think about climate, we are thinking on these really large scales, because that one little water molecule that is in your pond in the backyard could be picked up and taken halfway across the world over time and then deposited maybe even in a glacier. So the water that we have is fluid and moving around this system quite a lot. And we need to think about how these pressures affect each other. If we change the way that the ground absorbs water across a huge area, that's going to affect something somewhere else in the world. And so often when we think about ice, we think about things that are happening in Antarctica and in the Arctic in terms of those changes and climate change. We think, oh, okay, well, what can we do in the Arctic to make it better? How can I hold on to this iceberg and make sure it doesn't go anywhere? And I think the important thing when we look at the water cycle is to remember that it's a global thing. So what you do at home does matter. So this is another representation of the water cycle, a bit more colorful. And you can see here at the bottom, it does have that renewable groundwater and that non-renewable groundwater, showing you that more top active layer, and then below is that groundwater that won't get moved. Because over on the right, we can see the retention rates of the areas of where that water lands. So in deep groundwater, that water may remain in that place by the time it eventually gets shifted around by a number of pressures, 10,000 years. So I don't know about you or me, I'm not living 10,000 years, so that's not going to be replaced in a really long time. It's not going to move through that water cycle system for a really long time. The other big long retention time I want you to look at is the Antarctica continental ice shelf. And we're looking at 20,000 years for some water to move through. Obviously, this is an average throughout the system. We're going to have some things that are falling off on the sides really quickly, and we're going to have some things that are really deep in the center that are going to be retained for many, many, many more thousands of years. So obviously it depends exactly where, but on average, that's what we're looking for. And so we can see things that are really short, like the atmosphere is 9 days, that gas is moving around really quickly. And so where is the amount of water? This is another beautiful diagram as well. This just shows us the volume of water in the various distributions around the Earth. And we can see each column here is expanding from the column before. So the first column is the true amount. And if you have a look, we've got 96.5% of our water is in the oceans. They're big, if we didn't already know. And our freshwater only making up 2.5% of all of our water. We then expand that freshwater and we have a look at how that is broken up. And over 2/3 of our freshwater are held in glaciers and ice caps. So ice is really important as maintaining some of that fresh water, but also acting as some of those other climate drivers, and we'll talk about them in a little bit. We can see our groundwater there as well, making up a significant portion of our fresh water, and our surface water is really minimal. Our surface water is the thing that moves quite a lot. It's the thing that we utilize, it's more accessible, and it also means that we need to be careful with that little fragile layer that we have, because it's not all of it. And then also making sure that we maintain our ice, and then our oceans are going to be a huge medium for so much life as well. So what are the types of ice? There are different forms that crystal lattice structure can form. I'm not going to talk about them. I'm going to really talk about our glacier ice and our sea ice. And it's kind of our freshwater ice and our saltwater frozen sea ice. So we're going to have a look at these two and how they differ. We do see them in the same place, and sometimes we don't see them anywhere near each other. So I'm just going to talk about some of the terminology here. When I refer to glaciers, we are talking about kind of rivers of frozen ice, and that's on land. So this frozen ice is freshwater, and it will be accumulating in various regions around the world, and then under its own weight will start to shift and move. It's going to be a slower rate than a liquid river, but it's definitely observable. Our sea ice, as I mentioned, is frozen ocean, frozen saltwater. And because it's saltwater, it has some really unique properties, which I'll dive into, and they're really important for our Arctic food web. Ice sheets are the mass of glacial ice, so our freshwater ice that are on land that extend for more than 50,000 square kilometers. So that's about just under 20,000 square miles. There's only 2 ice sheets on Earth today. Obviously, if we look back through our ice ages, there would have been other ice sheets, and I'll mention one later on. And so the 2 ice sheets today, we have the Greenland ice sheet and the Antarctic ice sheet. These ice sheets were much bigger in the last ice age, and there were a few others as well. So together, the Antarctic ice sheet and the Greenland ice sheet, they make up more than 70% of the freshwater on Earth, and freshwater ice, sorry, and over 2/3, nearly getting up to that 70% of the freshwater in general. The Antarctic ice sheet extends almost 14 million square kilometers, which is about 5.5 million square miles for those who like big numbers. And that's roughly the size of the US and Mexico combined. So yeah, pretty big. It's easy when it's right at the bottom of a map and spread out to not really picture how large that is, but it is a huge amount of ice. And The Greenland ice sheet is about 1.7 million square kilometers, which is about 650 odd thousand square miles. Um, and that covers most of the island of Greenland, as you can imagine. And good old Wiki has told me it's 3 times the size of Texas. So that gives you an idea of the size of that as well. In the Arctic, we have the Arctic Sea. So we actually see a lot more sea ice along with our Greenland ice sheet. Whereas in Antarctica, we're actually relying more on the Antarctic ice sheet than on the sea ice that will just form around the edge. So there are big ice sheets. Icebergs, they are often in the water. So you would be forgiven for thinking that we are seeing icebergs made of frozen sea ice, but icebergs are actually freshwater and they've come from ice sheets or from glaciers and they've come into the ocean. And so an iceberg can be that frozen glacial ice anywhere from the size of an ice cube up to the size of small countries. So huge size variation, but that iceberg has come from the land ice. And then we also have seasonal ice or seasonal sea ice. Seasonal ice is that sea ice that is only formed every year and sometimes every 2 years, but is turning over quite quickly, and it's really, really important for our Arctic food web because of its transient nature, but also because of its thinness compared to multi-year sea ice. And we'll go into that in a moment. So they're just some of the terms that I'm going to be using throughout. And we'll dive into glaciers first. This glaciation that occurs is a huge force. We just heard about the size of our ice sheets, but the glaciers themselves are heavy. They are really quite strong and coarse, and as they move under their own weight, they actually carve all of the rock underneath it. And this is why we see so many rocky moraines around our glacier areas. The weight of the ice, it generally needs to be bordering on 30, but generally once we're at 50 meters thickness or 160 feet, the stress on the layer above the ice will actually start moving that ice down. And so we do see a natural flow of glaciers, and we're assuming for a stable glacier that that flow downwards is being balanced by the amount of water that's falling above it. So we need that ice and snowpack to compress at the top to continue to renew that glacier. Now, I'm sure all of us here are aware that that is not balanced at the moment, and we are seeing glaciers reduce. They are moving down more than they are being replaced, and they're melting from surface temperatures as well, more than they're being replaced. And we'll talk about that at the end. That weight as well can be really strong to carve through. And if you saw my other Nature Decoders series on rocks, we would have looked at some of the impacts of our glaciation as those glaciers carve out mountains. And we do see these glaciers around the world. This one is in Iceland. The photo before was in Greenland. We see them all across Earth. My closest, I think, would be New Zealand now. I think there's no tiny ones in Australia anymore. And we see about 10% of the land area on Earth is covered with glacial ice. This is mainly our ice sheets, but we do have glaciers around the world. And it can be really, really awesome thing to see. And often when you go to these smaller pockets around the world, you may see photos as well of what it used to look like. It's a really observable way that we can see the world changing. And through that climate change, the glaciers are really, really delicate. They're really important indicators of how they preserve themselves and what that indicates for the environment. So in this photo, we can sort of see the land behind is not covered in snow at the moment. So it is relatively warm. We see this beautiful clear blue coming through when we're seeing quite a lot of the top layer of snow or less compacted ice is melting off. And so the evaporation that happens on the glaciers will change depending on the covering of the snow on that glacier. So if there's a nice white blanket of snow, that's going to reflect a lot of the light and it's going to allow the ice underneath to stay for longer. But once we lose that top layer of snow, it's easier for the rest of the glacier to start to feel that heat of the sun. So the color can also determine how much that glacier is shifting. The air temperature obviously is something that we're going to see of that melting, and then how much precipitation in general is falling at the top. So we have a number of different factors that are changing the way that these glaciers melt, and they become these really, really sensitive indicators for us. And these were one of the first things that I think a lot of general people outside of the science community could see really early on in these stages of climate change. This was a really big wake up call for a lot of people. And we've seen that happen over the past about, 50, since the Industrial Revolution, but then really especially in the past 50, 60 years. And yeah, so it's a really, really delicate, beautiful indicator. When that glacier does continue to fall down from those snow-covered peaks down through the water, and then sometimes it will come out into the ocean. And that's when we see our icebergs. So as it's doing that, it is carving the ground beneath them. And if anyone saw my rocks, you'll remember this. As it carves through, it then just drops the deposits of the rock that it breaks up, and it doesn't sort them. Rivers, when they sort rocks, they sort them in the size of largest at the bottom and then, silty at the bottom and then large at the top. So you can imagine if you're sifting flour or if you're panning for gold, the water is going to help and the movement is going to help sort through these layers. But glaciers just drop everything. And so you can see this. This is in Australia when we did have glaciers. You can see this glacial till, which is this unsorted rock. It's got big chunks of rock and then this really fine silt. And that can show us where the glaciers have been throughout our geological time frame. And we also talked about the U-shaped valleys that we see. We see these massive U flat-bottomed domes as these glaciers push through because we're looking at this larger volume of solid ice as opposed to a carving river that'll make our V. So they're the features that we can see in our landscape. We'll also see these beautiful turquoise or blue lakes. This is Lake Louise with a beautiful Victoria Glacier behind. And we see this as a really characteristic color of our glacial lakes and our glacial rivers. And as these glaciers are bulldozing their way through the rocks and they're crushing them up, it does also produce like a really fine sediment that's left over. And so as the water picks it up, the heavy stuff sinks to the bottom, and the really fine particles remain suspended in the water. And we call these fine suspended particles glacial flour, like the flour that we're sifting, which I think is a quite lovely name. But what happens with those really fine particles that are suspended, and they do vary in composition depending what rock has been ground up, but the light will react differently having those particles. So you can imagine having something cloudy in a drink and then it's settling out. It's the same thing, but here we're seeing those particles are absorbing the really short wavelengths of light. They're absorbing our really deep purples and our indigos. And then the water itself is absorbing a lot of the longer wavelengths. So these are our reds, our oranges, and sometimes our yellows. And so that leaves quite a narrow range. It leaves our greens and our blues, and that's the color that we're seeing. So when we're seeing this color, that's what light is left. And it's because of that glacial flour taking out the deepness of the blues of the water that we often see. If you think of a deep blue ocean, but you add this glacial flour in, and we also take out that deep blue, and so we're left with this beautiful, quite light, almost creamy turquoise blue. We'll see this blue as well when we see our icebergs or our glacial ice as like an ice cave without that snow. Here we're not seeing as much glacial flour mixed in, as opposed to more of an absence of white. And the white that we're seeing is often just air. And that air is refracting the light in every direction and breaking up that light so that we get every spectrum of light back and it appears as that white. And so we see that in our snow, but also in bubbly ice. And so when that starts to melt off, and when we get to the denser, less air prone ice in the center, we see that really beautiful kind of clear blue color. And I went over to Newfoundland on a holiday one time, and they had all of these beautiful local drinks they had over like 34 species of berries and beautiful herbs. It was lovely. But they used to also have a gimmick of having some iceberg ice when it came by in their drinks. And I was talking to the bartender there, and he said he hated it for drinks because iceberg ice is often full of air bubbles. And if you have a ice cube in your drink that's got lots of air in it, it melts really quickly because it's got that increased surface area. So it's going to melt much more rapidly than more solid ice. And they did switch that out. So I thought that was an interesting application when we looked at iceberg ice. But it is something to bear in mind. We had this ice that was nice and stable on land, and then it falls into the water. And now, obviously, we're getting a warmer water, probably moving with the currents into areas where the atmosphere is warmer. And any of that air or any of those little nooks and crannies are going to assist in this iceberg melting a little bit quicker. So the icebergs make it to sea, as I mentioned, they can vary in size. In terms of iceberg definition, it can be a massive chunk or it can be a tiny little ice cube. We see them floating because we know that they're less dense than the water below them. And they can be really helpful for us to understand what is happening in the climate in general and also what's happening on land. We can look at how these icebergs have carved away from the ice sheets or the glaciers and how they break up. We can often see a difference between our icebergs and our sea ice depending on where we are. So if we think about where the ice could have formed, that can inform you of whether it's iceberg or sea ice. Things that are really large, massive chunks, generally, in this photo, there's land behind. You're going to know if you're in Antarctica or Greenland. So that's going to give you a really good indicator. But you will sometimes see a mix of the two. And around the outsides, we're obviously going to have a slush of the both. But we're going to shift over to talk about sea ice now. So sea ice is our frozen salt water, not fresh water. And because of the salt in the water, it actually changes the freezing temperature. So rather than our normal freezing temperature of water, 0 Celsius, we have a freezing temperature of about 1.8 degrees negative. Sorry, I said that really weirdly. Negative 1.8 degrees Celsius, which is about 28.7 degrees Fahrenheit. So it's a little bit below our normal freezing temperature. And the way that this freezes is often determined by the number of days that the water has been below freezing temperature. So if the water is really, really cold, it will freeze more rapidly. Makes sense. Than if it's, just a little bit below freezing for a number of days. So you can speed up or slow down that process. And we see that when we see sea ice formation. And here we're looking generally, it's going to be forming in more flat sheets, but it does also get pushed around by the currents, by the wind and the waves, and other things that are running into it. So whether it hits some landmass or if it hits some other ice, it can actually thrust that ice upwards. So we can see sea ice that is really quite tall. We can get massive 10-meter sheets that have been pushed up and become these ridges of ice. But generally, we're looking across this more flat landscape. So this is over in Churchill in Hudson Bay when I was guiding for polar bear season. And this was really exciting. This is just a little phone snap out the polar rover window because I was starting to see the ice freeze up. And I'm sure if anyone's done our polar bear expeditions, we'll talk about ice quite a lot. And the freeze up is so exciting. It's like the best time of year for a polar bear. And therefore, it's the best time of year for me as well. I was so excited to see this coming in. And it shows some of the ways that the ice forms because it doesn't just form in this one easy set way. The ice, as it's getting cold, these crystals are trying to form. There's all these things in the way that you don't have to consider when you're high up on a glacial mountain. And so you're looking for trying to grow these crystals, but then you get knocked about by the waves and the wind, and you get then becomes this sort of slurry, this slush of ice crystals that haven't quite connected yet. And so we go through these different stages of new ice as they form. And it can stay in this slurry phase for a while, and then as soon as there's a still day, there's no wind or there's no big current, or it gets really, really cold, there's a cold snap, then what looks like liquid water can be just on the tipping point of turning into ice, and we can see huge amounts of ice form in a single day. It's really quite special. And so we can see here, like, we're seeing a little bit caught where there is a spit of land behind, and it's a little bit more still so that ice can form a little bit bigger. But then only a number of days later, we started to see a full ice shelf extending out, some places even up to a kilometer out. And so it really does tip quite quickly. It's quite fascinating to watch as that changes. And you can see live satellite ice updates around the world. And we saw that as we saw the ice break up in the north this season. Obviously, us polar bear guides have always watched that ice very, very closely. And I'll talk about that later because there was an interesting thing that happened this year. So there's lots of different definitions of ice as they form, the different forms that they take. The fragile ice is really, really small. These are like individual clusters of crystals. And these are the first little bits of new ice that form. They're suspended still in the water, and they become then that slush. And then they can move on to a thing called grease ice. And it really does look like grease if you see it. It looks like there is this soft greasy layer suspended on top of the water. And that is really, really small, broken apart parts of ice. We then form these pancake ice sheets. This is not really the greatest photo of that. These are some more broken up sheets, but you will get rings with extended edges as the waves are lapping up and forming an edge on that pancake. And then we'll actually form our nihilus ice. And so all the things above, they don't form a consistent crust, but once we get to our nihilus ice, going up to our 10 centimeter mark in thickness, which is just under 4 inches, then it starts to bend without breaking with the waves or the wind. And so it becomes a more consistent sheet. And then this nihilus ice will then grow up to be young ice, and that young ice is between 10 and 30 centimeters, about 4 to 12 inches. And then that young ice, as it thickens, then it becomes our first year ice. Our first year ice then extends obviously into our second and our multi-year ice, if it lasts that long. So this ice is growing from these ice crystals, but we do have salt in the way. And so the salt actually interacts with our sea ice formation in a really interesting way. Because it pushes the water molecules are trying to fuse together. They have these bonds that they're trying to maintain. And so they start to push all the salt water into little pockets as they freeze. And so we start to get these super concentrated areas of salty water. There's still a bit of water to have that salt soluble in it, but they produce these brine pockets or these brine channels. And so this really concentrated amount of salt will change the freezing temperature, and they'll maintain these channels where the ice won't be solid all the way through. And so this causes sea ice to be really porous, has these channels through it, has this really amazing texture to it. And this is really, really important. We also have these growing crystals underneath. And when the ice is of a certain thickness, we're looking at our young ice and then our first year ice. It also allows light to permeate through that ice. And that light being able to get through the ice and through those channels and this rough, broken up surface underneath is the best growing media for our algae. And the algae are the start of our Arctic food web. And so this sea ice, because of the way it forms, and it's not going to happen with our glacial ice, is really important for our Arctic food web, and everything depends on it. So this is a really beautiful diagram of our Arctic food web, and it shows all of our lovely critters under and above the ice, obviously all the way up to our humans and polar bears. But we need that surface, that substrate of the thin ice. And you can see on this diagram where it goes from that first year ice into that multi-year ice, it's harder for that ice algae to grow. And so that ice algae becomes really, the grass, the plants, the basis that we would imagine for a on-land terrestrial food web. That then feeds our zooplankton and our small crustaceans that feed our fish and our seals and our whales, and then all the way up. And so we start with this beautiful grass, except it's upside down. It's on the top of our sea ice surface. And this will then become an amazing catalyst for all of the life really in the Arctic. And so maintaining this level of sea ice is really important. The sea ice is dynamic, it doesn't just stay put, it does break up and change over time. And those interplays between the surface and the ocean are really important. So while it will form this big sheet, there are massive currents happening. It is still shifting and moving around. And this is really, really, really important. You can see the difference in thickness here. And so that will support different communities of algae underneath. So a really, really intricate and important web. I won't go into too much detail because I could talk about that all day. But you can see why it's so important that polar bears get out on there. You can see this beautiful cub of the year, a koi, playing with a hunk of ice on land. So excited for the ice to start to come in. And then they can head out and they can begin their life on the ice. So what about down under me, in Antarctica? What's the difference here? We're not seeing as much sea ice because Antarctica is more of a landmass and the Arctic Ocean has more of our sea ice formation. It doesn't stay as long in Antarctica. It then comes out into open and warmer oceans. So typically our Antarctic sea ice is only about 1 to 2 meters deep, 1 to 2 meters thick, which is about 3 to 6 feet. And then our Arctic ice can get a little bit thicker, typically 2 to 3 meters or 6 to 9 feet. So we're going to see a difference there. And it also means we see a difference in the algal communities they support and therefore the entire food web they support. You see different species across there, as well as obviously the spatial range being really far away. And so, yeah, it's really, really interesting to see how they change, what species they support, but also how important and how in flux it is. We need this like delicate transient balance of this young sea ice forming and then disappearing and then coming back. We need that flow. So, what are the impacts that we see of ice around the world? I wanted to talk about one example of the power of ice. We're talking about a lot of them already, but one really cool thing that we do see is how heavy ice is. Yes, it's less dense than water, but it is very, very heavy. So we did have another ice sheet over most of the northern US and most of Canada, which was the Laurentide ice sheet. And the Laurentide ice sheet sat over this area of the continent from about 2.5 million years ago until it started breaking up. And then as things got warmer, it lifted. But what it did is it actually compressed the entire landmass and it pushed the rock, pushed the continent down. And so now that that Laurentide ice sheet isn't there, we're actually seeing the land rise in some of these areas. We see this in a few areas in Antarctica as well as a couple of little pockets around the world. And this is what we call isostatic rebound or post-glacial rebound. And this is where the Earth is actually rising up now that it can stretch after that ice sheet has come off it. And this map here shows us the densities, the highest areas where that vertical crust motion is happening. And I put this photo in here because of the boat on the shore. This boat has been moved, but what we can do is we can actually measure the rate at which this isostatic rebound is lifting up by things like mooring rings. We can even look in Churchill, there's mooring rings that are now several meters up on the shore, and you wouldn't want to put your mooring ring away from the shore. And that's because over the past hundreds of years, the shoreline has shifted and it has risen up. So this ice is making a massive difference to this area of the world. You can see it's not true all over the world, but it's one of those factors. And so what are the other things that are happening? We talked about some of the changes and why sea ice is so important, why glacier ice is so important. I hope that hits in. But there's also some other factors that will start to feed into some cycles that we need to be aware of. And so as those changes are happening, we talked about glacial ice being really delicate and really sensitive to those changes. We'll also see this with sea ice coverage as well. So there's an effect that we have called the albedo effect. And you can see here, obviously, our beautiful white substrate, our snow and our ice reflects a lot of that solar energy, a lot of that heat. And without it, it gets absorbed into the water. And as that gets absorbed into the water, that water is actually increasing in temperature. Because it's that dark color, it's actually absorbing most of that light and it's increasing the rate of warming. So we're starting to see these feedback mechanisms kick off. And this is why we're really concerned about limiting our impact as soon as possible. We're already seeing devastating impacts, but those impacts can start to exacerbate and build on each other because of some of these feedback loops. So if we lose more of the sea ice, we're going to get even more warming faster, which means we'll get less sea ice, which means it'll warm faster. So we get this continual feedback loop. So it's really important that we try and do what we can. And another feedback that we have is our methane release and also our CO2 release. And there's some really cool new work looking at the carbon cycle with ice. We see this with our ice algae and our food web, because that food web is actually an active process of moving carbon around. But we also have ice that has capped and stored previous gases. Methane and CO2 are quite heavy, but they're also products of previous vegetation use. And so when we saw like peatlands that then got covered in glaciers, we can have huge stores of carbon and methane that have been trapped. And when that ice melts, it's going to release it. And so we see our methane concentrations in the atmosphere are about 8 to 10% higher in the Arctic than they are in the Antarctic atmosphere, based on what was trapped, but now also what is being released. And we can see that release. So I'm going to talk a little bit about what we're seeing today and the sea ice that we're seeing at the moment. It's 2024 and we've just passed our minimum ice. So we've started to see all of the new stats come out from that. And we can see here, this is from satellite data. So this is from looking over at the satellite extent of our Arctic sea ice. And we can see that since 1979. We have many other records that extend further back. We can look at a lot of different atmospheric and indicators in glaciers themselves, as well as in the rock and like that shoreline, but we can see that with glacial recession as well. So we have other indicators before 1979, but this is from some really, really amazing data. And it does show a really clear trend decline. I want to point out in the last 20 years, so if you go to 2004, you can see that all of those have been below the previous years. So yes, we see fluctuations year to year, but all in the past 20 years have been the lowest on our record. So we're seeing about a 10% to 12% decline a decade, which is huge. And it is really measurable, it's really easy to see. And so it's something that we really need to be acting on. This is from this year. You can see the minimum extent, so when it got down to its lowest, and then it's compared to the median ice edge from 1980 to 2010. Now, that's the median average, and as we know, that average is going to continue, that median is going to keep shifting as we add years to it, but they've kind of stopped it at 2010 as a baseline. And you can see that all of the ice that was left is less than that pink outline. In Churchill, for those who want a Churchill update, we saw across the Hudson Bay, we saw a really interesting thing happen in June, July, where there was huge currents and winds that actually broke up majority of the sea ice on the east side of Hudson Bay. And so there was a huge area of open water much earlier than we've ever seen. And the western side maintained its ice. And the western side actually maintained its ice for a lot longer than we've seen in the last few years. Obviously, we are still trending downwards, but we did see quite a lot of ice on the western side. So in terms of polar bears, we've been excited for extended ice on the west, but it means the polar bears who occupy the eastern side of Hudson Bay would have had a really tough year. So we can see these fluctuations and we see these ebbs and flows. We are seeing these trends over time. So yeah, it's important. I'm preaching to the choir here, but yeah, we are seeing these trends even when we do have a good year. So that's something we need to be acting on. Apart from our sea ice, you can see our sea ice, Arctic sea ice is making up a huge percentage of our loss here. We're also seeing the glaciers are receding, as well as the ice sheets themselves. So in the past, oh gosh, not even, yeah, 30 years, this is only up until 2017, but we're seeing about 22% of Earth's ice is lost during that period. That is huge numbers. This is not just like a little bit of a difference that we can see that is coming through. It really is quite startling impact. The ice is a really good indicator for us around the world. And so we're really calling on us to do something about it because a lot of nature can't do it for itself. And we can make a difference. And I know it can be hard when we hear these big numbers, and I've sort of come to the end on these big numbers, but we can do something about it. Don't lose hope. That's not going to help anyone. The changes that we've made over the past couple of hundred years specifically have all come from small changes that have grown into bigger systems. And so in the same way, we can make those small community changes and they can grow into bigger systems. And we're seeing it. There's a lot of really amazing stuff that is happening. And so keep doing what you're doing, keep advocating, keep educating, and just remember that it's a global system. When we look at this ice around the world, it's all linked to everything we do, everything in our backyard. So um, keep educating, keep advocating, vote with the climate in mind, and make those changes. And hopefully we'll have some amazing ice for a long time to come. Thank you guys. And if you have any questions, chuck them through.
All right, thank you, Nikki. Before we start with the question and answer session, I would like to remind everyone that you can submit your questions via the question field in your GoToWebinar control panel. And if you're interested in traveling with NatHab, you can visit our website at nathab.com for trip details or give us a call at 800-543-8917 to speak with an adventure specialist. All right, let's dive into some of these questions. So I think all of us want to know what happens to a polar bear that gets stuck on an iceberg that is moving away from land.
Okay. We're gonna say sea ice and not iceberg. Although yeah, they can be on both, but I'm focusing on my Churchill bears because that's where my heart is. They can be on icebergs that come off, and if they're lasting for a longer time, that's great because it's going to be a little bit colder. The sea ice is where their food web is, though. The sea ice is that interplay with the seals, and that's their main food source. We are seeing some polar bears that are actually shifting their food to some freshwater fish. But the fat content in those freshwater fish are not really great enough to sustain the bears. So we are still learning and investigating how polar bears are adapting to these changes, whether or not they have enough time to figure out another strategy of where to get food and what to do. The main thing is when that ice is away from land, we're talking about our Western Hudson Bay and our Southern Hudson Bay populations where they go back to land for the summer. But the bears up in other regions, so all of our 17 other subpopulations of polar bears, they can stay on multi-year ice and they can stay on ice sheets as well and icebergs. So they don't necessarily have to go back to land and they can hunker down there. But when we're seeing our Hudson Bay bears move away, they have to swim back to land. They have to get back to their denning areas and also be somewhere where they can serve that energy. They shut down their metabolism, and they slow down. They don't hibernate fully, but they do lounge around and relax. And if the ice is really far away, and it breaks up and it drops them off right in the center of Hudson Bay, or like this year we saw the eastern break up really quickly. So if there was a bear out there, they now have to swim a really long way to get to a stable area. And that swimming is really energetically taxing, and they lose a lot of their body condition. So when they start to lose that fat reserve that they've hopefully been building all of that winter and all of that spring, they've been trying to load on all this fat to make it through a lean time. They now have to spend all of that energy swimming, and it means that they're in a worse condition for the next year. That can have implications for themselves, but it also has implications for their offspring. We know females will produce fewer cubs if their body condition is less. They're trying to conserve themselves, so they're not going to produce an offspring if they're not feeling healthy enough. And they'll hope that next year they can do it better, get more fat on, and then have more cubs. But if we see this continual decline, we don't see that natural fluctuation. So it is concerning if the bears have to go further. And yeah, they're just going to be burning a lot more energy.
Great. Thank you, Nikki. So, do brine pockets in the sea ice contribute to its buoyancy?
Yeah, they can. It can trap not just brine, but also air in there. So it can help it to float a little bit in terms of air that's trapped in there. Trapped water itself is actually going to make it heavier because it's denser. But because it's cold, it's often not the densest part of water. So it's generally the air and the crystal of the ice itself, whereas the water is going to be a little bit heavier, but it's often not just water, it's other things. And it also can be a little way that little zooplankton or little crustaceans or a number of different organisms can move into these areas because they're able to move through it rather than the solid ice. Sometimes they expand those pockets as well, so that can also help. But generally, it's just the ice structure, the fact that it's a crystal structure that's going to help it float.
Great. Thank you. So, I think there's a little confusion here on some terminology. It Can you explain the difference between sea ice and iceberg? And is there a specific name for small icebergs? We've had a couple of questions. Some are saying berglets, some are saying bergy bits. Is there anything
Bergy
specific?
bits. I think there would be quite a few different terminologies around the world depending on what language that you're looking at. In terms of like true definition, an iceberg is really, it's still anything that's a freshwater from land ice. So anything that's glacial ice or that continental sheet ice that has fallen into the ocean is going to be an iceberg. So even if that iceberg is a bergy bit, which is a term that a lot of people do use, there's also things like growlers and things like that. So there are common names for different sizes of icebergs. And they often come from various ways in that, the way that our language has developed, and also in different areas around the world with the relationship of it. So if an iceberg serves a purpose of being able to stand on, or like there's resources there, versus if it's going to destroy your ship, these are often things we need to name, and so we do see a lot of those names. But our icebergs, they're going to be our freshwater, and then our sea ice is going to be frozen saltwater. And that really is the main difference. It can be hard when you're at the edge of a continental shelf and there's sea ice forming to tell the difference sometimes. But what I'm looking for in icebergs, it's really, I should know where I am, that I'm closer to land. And down south in Antarctica, we're going to see a lot more icebergs than sea ice. If you see those beautiful striations of that sediment or that silt going through in those straight lines, that's going to be from that iceberg carving on the land when it comes out. And so if you see that in the ocean, you're like, okay, that's definitely freshwater, as well as the really, really big ones, because the sea ice generally isn't going to be that big. But icebergs, freshwater, sea ice, salt.
Great. Thank you for clarifying that. Can
Nice.
you describe the difference between ice sheets and glaciers?
Ice sheets are glaciers. So glaciers is the general term for that freshwater land ice. Ice sheets are the specific large culminations of that glacier ice. And so the ice sheets need to be over about 50,000 square kilometers because that's the border that we've determined. And so they're just the really, really large areas of glacial ice. And we have two at the moment. We have the Greenland and the Antarctic ice sheets, but we used to have others. And the example I gave of that compression over Canada and northern US, that was the Laurentide ice sheet.
Gotcha. So, do we know where that large iceberg, the size of Rhode Island, that broke loose, do we know where that's traveling? Is there any danger of it causing any damage? And can we stop it from moving?
Um, I don't know the specific iceberg because I haven't been following it. It's a little far away from me, so I'm sorry to say it's not quite on my radar, but there would be people tracking it, I would imagine. Often those flows that come down across the eastern side of Canada and then down towards the US, we know about them for some time. There is potential for damage. Hopefully, we can track it well enough now that it should be avoidable in terms of shipping routes. Um, Generally, that's really quite heavily embedded in our navigation systems. Um, and if it does come towards land, there hopefully should be enough warning. I just don't know the specific movements of that one. Can we do anything about it? I mean, probably. Do we want to do anything about it? I think if we can move our way around those sort of events, then that's always great, rather than trying to influence it. I don't really want to set a precedent of going up and breaking up all the icebergs because we need that to actually keep things a little bit cooler. So I'm not sure on that specific one, but I'm sure there would be ways, and I'd have a look if there's any local marine authorities. That'd be the place to look.
Great. Thank you. So, if I'm headed up to Churchill, say this October, can you give us something specific, or is there anything in general that we should be looking for?
Oh, oh my God. Everything's going to be amazing. I'm so excited for you. I want to come with you. Do you have room in your suitcase? Is there anything you should be looking for? If you want to look for, get your ice knowledge up and kind of shock your ELs a bit to be like, oh, they know about sea ice. Um, you can have a look at the data from the National Sea and Ice uh, Center. They have some really cool stuff. And you can look at what the ice did this year. If you're going up to Churchill, I'd recommend looking at what happened over the breakup just recently, where we had that west and east divide. And knowing about that is already going to be really cool. Depends exactly when you go in October and then into November, and it depends what the weather is happening. But you'll often see a little bit of sea ice starting to form in those protected areas before it fully extends out. And so I urge you to have a look at that ice a little bit closer and see how it forms. But you're going to learn so much there, and I don't want to take it all away from your expedition leaders. You're going to see so much. The town itself is so beautiful. There's a lot of amazing wildlife. If you go later in the season, one of my favorite times to go was actually late in the season because that ice started to form up and we saw bears and they were further away. And so you're like, oh man, the bears are so far away. But we also got to see the bears swim and interact with the ice because they're waiting for the ice. They're so excited to be there. So even if they're a bit further away, it's usually because they're really happy and I'm really happy for them. And yeah, I just had one of the most magical times right at the end of the season as well. So um, there's a trade off between having bears nice and close on land versus having fun in the ice. Um, yeah, it'll be amazing.
All right. Thank you, Nikki. Unfortunately, that's going to be our last question for today. So I'd like to throw it back to you for any closing comments you may have.
Thank you, Rob, and thank you, everyone. It's been a real delight to talk about ice today. I hope you all have a little bit of inspiration to think about our global water cycle. We run so many ice trips around the world, including our inland glaciers as well as north and south. But yeah, just remember it's a big system. We're all part of this world together. We can make a difference, and we are. We just need to keep pushing. So don't lose hope. As a young biologist and guide, I'm happy to always keep pushing and keep educating in this space, but also just share that with your local community. And then hopefully we'll have ice for a lot longer. Thanks, guys.
Nikki, thank you so much for taking the time to present for us today. And I'd also like to thank everyone who tuned in today. So if you're interested in information on how you can travel with NatHab, give us a call at 800-543-8917 or send us an email at info@nathab.com. Our adventure specialists are happy to help you out. Join us tomorrow for our next daily dose of nature. You can check out this week's lineup, including registration links, on our website at nathab.com/webinars. We did record today's presentation, and we will have the replay available on our website soon. With that, I will conclude today's webinar. Goodbye, everybody. We'll see you next time.